Okay, so today we're learning about power series. Here are some power series that you might remember from Calc 2. You can write those down and just memorize them. I think the first three are the most important. I think those are the ones your professors might pull out. I know where these, if they pull these out, then they're just really mean people. But knowing them all would be helpful, right? Let's get a sense of how we derive them and how we might derive any power series for any function, or at least the first several terms. Let's derive the power series for e to the x. Naturally, sine of x would be better. So what you're going to do is you're going to write the function f of x equals sine of x off to the side, and you're going to take enough derivatives so that you can recognize the pattern that's going on. So I'm going to take the first 5 derivatives. I know it seems excessive, but sometimes you do need to take a lot of derivatives to figure out the pattern. We're trying to find a power series representation for sine of x. Fifth derivative would be cosine. Okay. We're going to find the power series for sine for f of x equals sine of x, centered at x equals 0. So what that means is, once we take those first, however many derivatives we'd like, we're going to plug in 0 into all these derivatives and figure out what we get. When we plug in 0 for any sine of x, we get 0. So 0, 0, 0. And when we plug 0 in for cosine, we get 1. So we get a 1 here, a negative 1 here, and a 1 here. Now these are like the DNA of your power series. These coefficients uniquely determine any given power series. So if it was 1, 1, 1, 1, 1, 1, that would be e to the x. If you get 1, 0, negative 1, 0, 1, negative 1, or maybe it's back to 1. In any case, that gives you cosine. But so basically it's kind of encoding a series. And the ones that correspond to 0, 1, 0, negative 1, 0, 1 is sine. We'll see how that happens right now. You start by f of x. You always just write the first number in your list. 0. So whatever the first number in your list is, you write it down. Then you say plus the next number in your list. But because it's the next number on our list, we're going to say times x minus 0 to the first over 1 factorial. I'm saying x minus 0 because it's centered at x equals 0. So keep in mind if it was centered at x equals 2 or x equals negative 3, I will have it changed accordingly. Okay, the next term. What's the next number in my list over here on the right?
0.
0. We're going to say times x minus 0 now to the second power over 2 factorial. Next number on my list is negative 1 times x minus 0 down to the third power over 3 factorial. Next number in my list is 0 times x minus 0 to the fourth power over 4 factorial. And lastly, plus 1 times x minus 0 to the fifth power all over 5 factorial. Now, you probably could have saved yourself some time and not written so much, because we know that terms that have 0, when they're multiplied by 0, they just go away, right? I like just writing it all out right now because it gives me a clear method. Okay, my last term was 1, now my next term is 2, now this next one is 3, now the next one's 4. I won't make a mistake of, like, if I had said, I'm going to just deliberately ignore that because I know it's got a 0 in it, I might have thought to put a 4 here because I've had a 3 there. So I just like writing it all out so I don't, being very consistent, so I don't lose anything. But we all do know that these go away. Yeah. And so this simplifies to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And you probably can take a stab in the dark as to what the next term in that list would be. How would you guess?
7 or...
Well, minus x to what? X to the 7th over to the factorial, right? And so we're kind of gleaning a pattern here just by taking a few derivatives. Let's make that pattern succinct and put it in a summation. So we're going to say n equals 0 to infinity. What kind of powers do we have here? 1, 3, 5, 7. Odd numbers are 2n plus 1. Even numbers are 2n, right? That's something to take to the bank if you'd like. 2n is even, and 2n plus 1 or minus 1 is odd. So x to the 2n, right? And we also notice odd factorials. So we're going to have a 2n plus 1 factorial. What other pattern am I recognizing here? Is also part of my series?
The sign.
Yeah, it's, all right, the sign is changing. It's alternating. So we're going to put a negative 1 to the n. Now, if you ever feel unsure that your pattern matches, or what you derived as your sum matches the summation here, you can always test a few values. Let's say I chose n equals 2 here. Plug in 2. Now, this would be n equals 0. This would be n equals 1. This would be n equals 2. So when I plug in 2 for n here, I should get this term. What's negative 1 squared?
1.
Positive 1. 2 times 2 is 4 plus 1 is 5. 2 times 2 is 4 plus 1 is 5, so it does match. If you want to do one more time, you can do one more time, like pick n equals 3, and you'll see that you'll get this term. And so you're like, okay, I feel pretty confident that that's my power series. And then sure enough, it is what I have written over here, right? Cool. All right, now, that's how you construct a power series. So in case your professor ever asks you for any reason to construct a power series, follow that method there. Find a power series for some function centered at a certain value. You take as many derivatives as you need to in order for you to figure out a pattern. And once you've got a good pattern going on, then you can make a nice summation out of it. One other thing I want to mention, sometimes they just say, find the first 4 non-zero terms, in which case, well, let's say not first 4 non-zero terms, let's say the first 3 non-zero terms. Well, this is 0, 0, 0, so these don't count. As much as it looks like we've gotten 1, 2, 3, 4, 5, 6 terms, the problem says we want the first 3 non-zero terms, so these don't count. And so we do have this one, this one, this one, and so we'd be good. And you actually just put this as your answer. You're not expected to create the series, the corresponding series. They just want the first 3 terms and call it a day. Good? All right, let's talk about finding the radius of convergence, an interval of convergence for a series, and then we'll move on to solving differential equations with them in a minute. Just in case, you're starting from scratch with power series. Suppose I gave you a series like -1 to the n times x minus 4 to the n all over 7 to the n. Let's say 3 times 7 to the n. We'll do another one as well. Okay, I probably should start with equal 1 there. Okay. If they ever ask you to find the radius and interval of convergence of a given power series, they say, hey, boom, there's a power series. Find the interval and radius of convergence. We can use the root test or the ratio test to go ahead and find that. You tend to use the root test when you see a lot of things being raised to the n, which would work here, or use the ratio test. Does anyone have a preference? Does anyone like the ratio test more than the root test, or the root test more than the ratio test? What's your test? What's your go-to test?
The ratio.
Ratio test? Okay. We'll do the ratio test. What do you like the root? Oh, wow.
I don't remember. We can do that one for that, and then we can do
okay, yeah, we can switch it up. I can actually just do both. So the ratio test really quickly. Ratio test is just a sub n plus 1 over a sub n, absolute value. Whatever we get from this after we take the limit that then goes to infinity, we want to be less than 1 in absolute value. So let's take a sub n plus 1. That means we're taking this entire term, but instead of, for every instance of n, we have n plus 1. Actually, with that in mind, I want to change this just a little bit. That's fine. That's fine. Is it, though? Let's make it interesting. Yeah. So change that 7 to the n to 7 to the 2n. We're going to replace every instance of n by n plus 1. So that means this becomes limit as n approaches infinity of, because it's inside an absolute value, you can write the -1 to the n. Just realize it's just going to go away, because the -1, when you take its absolute value, just vanishes. X to the n plus 1, I should say. But again, you know what? I'm not even going to bother writing the -1 to the n, right? Because it's inside absolute value, no point in writing it. We're going to get rid of it. So we have x minus 4 to the n plus 1 all over 3 times 7 to the what power?
And 2n plus 2.
2n plus 2, good. Yeah, this guy here. So I changed that to an n, right? I want to make sure you guys don't mess this up, though, because it might be tempting to say 2n plus 1, right? Because I said to replace every instance of n by n plus 1. But because you replace that instance of n by n plus 1, the 2 is distributed to both the n and the plus 1, so it gives it a 2n plus 2. So it's good that you caught that. All over. The nice thing is you just copy this term. So you just copy the term that's in the series. All right, let's clean this up a bit. We have x minus 4 to the n plus 1 over x minus 4 to the n. By dividing by this bottom fraction, I'm flipping and multiplying by the fuck me. It just does this. It just stops recording. No, it's still recording. What? All right, I'm going to edit that out. So, for those of you watching at home, there was a glitch. Don't worry, I swore a lot. Okay. So, x minus 4 to the n plus 1 over x minus 4 to the n. I'm going to group this 7 to the 2n, 2n plus 2. And we have a 7 to the 2n on the numerator. The 3, you can have a 3 over 3 if you'd like, but we know those cancel. X minus 4 to the n plus 1 and x minus 4 to the n cancel in such a way as to leave you with an x minus 4. And 7 to the 2n divided by 7 to the 2n plus 2, how do those cancel? They cancel in such a way that they leave what behind?
7 squared.
7 squared, exactly. So yeah, all the 2n7s that are here cancel with this 2n7s that are here, leaving us with 7 squared. So all over 7 squared. Don't forget, this is all still tucked on the inside of some absolute value. And we want this to be less than 1 in absolute value. Okay? Now, I don't know how you guys solve your absolute value inequalities. Some people just say, okay, here's how they tend to do it. Watch carefully. I'm going to drop these bars and put a greater than negative 1. That's how some people tend to do that. So if I see absolute value that x minus 2 is less than 3, then that's the same thing as x minus 2 is less than 3, but greater than negative 3. Okay? That's a really quick way of doing it. I'm going to multiply both sides by 7 squared or 49 to give me negative 49 is less than x minus 4 is less than 49. Then I'm going to add 4 to both sides to give me negative 45 is less than x is less than 49. So 49, 53 I should say, if I can add. Okay. We're almost out of the woods. Our interval of convergence looks like it's just negative 45 to 53, but you have to check your endpoints. So the question is, what would happen if I plug 53 in for x? 53 minus 4 is 49, and 49 to the, so if x equals 53, I get summation. 53 minus 4 is 49 to the n over 7 to the n would cancel, leaving me with just negative 1 to the n over 3. Does that make sense? The 7 to the 49 to the n and the 7 to the 2 would cancel because they're both 49 to the n. Okay, good. So one more time. 49 to the n is 7 to the 2n, those would cancel, just leaving me with negative 1 to the n over 3. What does this series do?
Alternates.
It alternates, I agree. When I plug in 0, I get 1/3, then I get minus 1/3, then I get plus 1/3, then I get minus 1/3. What does this series evaluate to? Does it have a sum? Does it eventually sum to a number? No. You could say it goes to 0 because it's 1/3 minus 1/3, so that's 0, but then you add 1/3 to it. And then it's going away from 0. Then it's back to 0, then it's back to 1/3, then it's back to 0. Those oscillate. It doesn't seem to be settling on a particular converging sum. So we say the series is divergent. And because of that, we will not be including 53 on our interval of convergence. We also have to check x equals negative 45. Checking, am I still recording? Okay, cool. If I plug in negative 45, I get negative 1 to the n times negative 45 minus 4 is negative 49 to the n. Over 3 times 7 to the 2n. How do these guys cancel? How do negative 49 to the n and 7 to the 2n cancel? They cancel in almost the same way, except they leave behind a what?
Negative.
They leave behind a negative 1 to the n, right? So you can almost think of it like this. This negative 49 to the n is the same as negative 1 to the n times 49 to the n. I'm pulling out that negative 1. This is where I made a joke in study edge. So I would say, guys, make sure you always remember to pull out, right? Haha. So the negative 1 can come out. There's still the 49. The 49 cancels with the 7 to the 2n down below, but I'm still left with a negative 1 to the n up here. That's fine. It really doesn't do too much of something too crazy. What ends up happening here? What is negative 1 to the n times negative 1 to the n?
1 to the 2n?
Negative 1 to the 2n. Right. So it seems as though you said, if I said 3 to the n times, I should say this, 3 to the 2n times 3 to the 4n. How do those multiply? 3 to the 2n times 3 to the 4n. It's not 9 to the 6n. It's 3 to the 6n, right? So you don't multiply the 3's that on the inside, you just add the exponents. Same thing here. Negative 1 times negative 1, you're tempted to multiply. You just had 1 to the 2n, right? Mm-hmm. But it's to remain negative 1, in much the same way that it remained 3 as I moved that. I was like, 16. But see how it doesn't become 3, or it doesn't become 9 to the 6n, even though there are 3's being multiplied here? Just keep that in mind. It will be negative 1 to the 2n. Now what is negative 1 to the 2n? 1, right? Because 2n is always an even number, and negative 1 to an even number is always going to be 1. So we just get 1/3, right? So we get 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 forever, which clearly diverges. It certainly doesn't settle on a number. So negative 45 will not be included because it causes our series to diverge. So our interval of convergence is negative 45 to 53. And notice I'm putting parentheses on the interval because I don't want to include either of those endpoints. It causes it to diverge. Those x values cause it to diverge. But if you pick any value of x between negative 45 and 53 and plug it in for x into this series, your series will converge, and if you pick anything outside of that interval, it will blow up to infinity. Cool? All right, let's do the other one, and then we'll move on to solving differential equations. I guess I thought I was going to do a root test. We'll do a root test over here on this one.
So that was ratio.
That was ratio test. Really briefly here, root test works almost the exact same way. You take the nth root limit as n goes to infinity of a sub n, which in this case would be actually the absolute value of a sub n. Oops. The absolute value, of course, gets rid of the negative 1 to the n. You get x minus 4 to the n over 3 times 7 to the 2n. Well, what happens here? When you take the nth root of x minus 4 to the n, you get x minus 4. When you take the nth root of 7 to the 2n, you get 7 squared. And this is just something true in general, and this is something that's really important that when you do root tests, you're going to see this happen a lot. The nth root, limit as n approaches infinity of the nth root of any constant is 1, and the limit as n approaches infinity of the nth root of n to any constant power is also 1. We're going to be using this for this next problem here. Now from here, you once again say less than 1 because you're trying to find convergence. And that's the criteria by which a series converges if you use a root test or ratio test. Same as ratio test as root test. Take this absolute value and say less than 1. But if you go from here, you get the same exact answer as we did before. Cool? So that's why I'm going to stop there on that problem. And move on to this one, where we'll do root tests more rigorously. So root test here, we take the limit as n approaches infinity of the nth root of the absolute value of 2x minus 3 to the n all over square root of n. The nth root there gives us 2x minus 3, absolute value. What about this guy? What's the limit as n approaches infinity of the nth root of the square root of n? Yeah, it's going to be using this idea here. Square root of n is really just n to the 1/2. So according to this formula, it'll tell you that the limit as n goes to infinity of the nth root of n to the 1/2 will be 1. Cool? So that's going to become 1. We say is less than 1 here because we're trying to find convergence. Absolute value of 2x minus 3 being less than 1 is the same thing as negative 1 being less than 2x minus 3 being less than 1. And solving for x there gives me 1 to 2. Once again, we have to check endpoints. So that looks, we're almost out of the woods. We have to check this right endpoint. So let's plug in 2. If I plug in 2 for x, I get, so if x equals 2, my series, well, don't know what happened, but it stopped recording. I have no idea why it does that, and I've always had a problem with that. But we're in the middle of doing root tests for another interval convergence problem. So keep an eye and make sure that it doesn't stop recording anymore. All right, we got to a point where we did the root test. Root test has taken us to 2x minus 3 over 1, because we're invoking the formula over here. The limit as n approaches infinity of the nth root of n to the k is 1. And that causes this guy to go, whoop, gone, becomes a 1. But we do have an absolute value of 2x minus 3 left over, which we want to be less than 1. Get down here, get down here. So here's our interval convergence almost. We do have to check our endpoints. If x equals 2, we plug 2 in for x here. We get 1 to the n, which is just 1, over square root of n. Now, here's where I want to ask you guys, what does this series do?
It diverges.
Diverges. Diverges by p-test, so I might have to harken back to Cal 2 for a bit. When you're looking at the series 1 over n to the p, this converges if p is larger than 1, and it diverges if p is less than or equal to 1. Well, because our power here is 1/2, this is n to the 1/2, that's less than 1, so this series will diverge. And because it diverges, we cannot include 2. We will not be including 2 on our interval of convergence. However, if we let x equal 1, we get this guy. Now, while it is true that summation from 1 to infinity of 1 over square root of n diverge, this one will converge. Do you know why this one converges?
Isn't that because of the negative it like
Right.
alters?
It's called the alternating series test. Now, you probably don't have to go through all this process, and I don't even know if they would give you something like this because, in short, here's what you need to remember: as long as the limit as n goes to infinity of a sub n is 0, then you're good. Technically, yes, for those of you watching at home thinking, there's another condition that you should check to make sure the series is decreasing. For the purposes of this class, they're not going to give you any limit that goes to 0 that isn't decreasing. Besides, how do you get to 0 without decreasing? Doesn't seem like it's possible. Unless you were increasing, but then the terms are negative, then you're not dealing with negative terms, so ignore that. All you need to check is that the limit as n approaches infinity of a sub n goes to 0. What's the limit as n approaches infinity of 1 over square root of n? 0. So, check. And it's alternating, so this will converge, so we can include 1 on our interval of convergence. Your interval of convergence will be 1 to 2. Good?
So, if the limit as n approaches infinity of a sub n does equal 0.
And if it does equal 0, which in this case it does, and it's alternating, the series is alternating, then it converges.
Okay.
Yeah, I didn't say that. I don't think I did. Then I think I just said, it does whatever, fucking great. It converges. That's the special thing, is that with this limit is 0, and it's alternating, then you know your series will converge. And so because this does converge, we can include that endpoint. Good? Cool. And that's the alternating series test. If you want to look up more, just look up AST or alternating series test. Alright. Oh, I didn't talk about radius of convergence, but it's not a big deal. Here's how you figure it out. How wide is this interval? 1. What's half that width? 1/2, right? That's your radius. Radius, if you want to do it this way, radius of convergence is just the width over 2. And a lot of people ask me, what do you mean by width? I just mean take the upper bound. So like if your interval is a to b, then your width would be b minus a, and then you divide that by 2 to get your radius. Okay. So for the last one, if you recall, what was our interval? It was like negative 45 to 53. The width of that interval is 98. Divided by 2 is 49. So the radius of the convergence of this previous series was 49. The radius of convergence for this series here is 1/2. Good? Alright, now we're done with kind of reviewing what power series are. That's kind of where you left off about power series in Calc 2. And now, we're going to figure out how to solve some power series, or solve some differential equations using power series. I'm going to start with something simple, and then we'll do your book problems in a second. So recording good. Alright. Well, let's see if I can make something up pretty well. Here we go. X squared. Let's do something small and easy to start. Although I might check my own work. 1 second. What's up, guys? Here we go. I like this instead. This would be better. I know I had better problems. Find the first 3 non-zero terms. First 3 non-zero terms for y prime plus, y prime equals y squared plus 3x. And then you're told y of 0 equals 1. Now, in class, you probably have seen your professors do the following. They start by writing the series, don't write this, summation n equals 0 to infinity, a sub n times x to the n. That's your general power series, and you're just going to memorize that. And one way of doing this is plugging this into here and into here, and then collecting terms and collecting powers on x and all that. We don't actually have to do that here because we're only looking for the first 3 non-zero terms, and we can do things pretty cleverly. We already have the first term, and actually we will kind of use this. We're going to say that our power series is this. a0 plus a1x plus a2x squared plus a3x cubed, and so on, which is just an expansion of this summation form, right? This is a condensed form, but if you start listing out terms n equals 0, n equals 1, n equals 2, then you'll get this, right? We already know that because y of 0 equals 1, what does it tell us about any one of these numbers? Well, what does y of 0 mean? It means plug in 0 for what?
Y.
Y of 0 means plug in 0 for x, and it gets what out for y?
Equals
1. So that means I plug in 1 for y, or when I plug in 0 for x, I get out 1 for y.
So a
Right, we know immediately that a sub 0 is 1. That's nice, right? So this is basically telling us, hey, that's a0. All right? Be careful because if your power series isn't centered at 0, like if they said, find the power series, find the first three terms of the power series centered at x equals 1, that's no good. It has to be 0, because when I plug in, if it was like, not that I ever imagined it would ever happen like this, but this could happen. Don't write this down, just 0 won't work here, right? Because 0, when I plug it in here, won't cause the A1 to go away. 0 here won't cause the A2 to go away. So that'd be a huge pain in the ass, right? Okay, sure, I'm still recording. Okay, cool. Alright, so just keep in mind that if it's centered at 1, then they better damn well give you y sub y of 1, right? Here, it's centered at 0, so we're going to be given y of 0. Alright, next thing is, because I know y of 0, basically when I plug in 0 for x, I can plug in 1 for y. I've been told that the coordinate 0, 1 is on this curve, and so it's got to satisfy this differential equation, y prime equals y squared plus 3x. So what is this telling me that y prime is? Y prime is telling me for free that I have y prime is 1. So y prime of 0 is 1. All right, how about y double prime? Does anyone see y double prime in this formula up here? No, but we can make it there, right? By doing what?
Deriving?
Yeah, differentiating is the word we use. Differentiating the left and the right side. When we do so, we get 2y. What's the derivative of y squared?
2y.
2y dy dx. Or, think of it this way. Think of y squared as being y squared. So we have to apply the chain rule. What's the derivative of y squared? Well, the 2 comes down in front, leaving the y alone. Then we multiply by the derivative of the inside. What's our independent variable here? X. We're taking the derivative with respect to x. So anytime the differential operator hits a variable that isn't x, we have to tack on a d that variable dx. Cool? So in our case, the dependent variable here is y. The differential operator hits the y squared and says 2y, which is now the first power, times the derivative of the inside function. The inside function is not x. So when we hit y with a differential operator, we have to say dy dx, right? Or dy dx, better known as y prime. Y prime. Cool. So this becomes 2y times y prime plus the derivative of 3x is 3. Okay. Once again, we know that when I plug in 0 for x, I get 1 for y, and I get 1 for y double, or for 1 for y prime. So I get 2 times 1 times 1 plus 3, so I know that y double prime is 5. And lastly, we're going to do it one more time. Or actually, no, we're good. First 3 non-zero terms, right? We got 1, 1, and 5, so we're good. Let's think back to what we did earlier in this review. We constructed the power series based on the first several derivatives, right? So, what's the first number? So let's get what it is. What's the first number on my list? 1. What's the next number on my list? 1 times x minus 0 to the 1 over 1 factorial. What's the next number on my list? 5. So I'm going to say 5 times x minus 0 to the second power, I should say, all over 2 factorial. So this boils down to 1 plus x plus 5 halves x squared. Before I go on to the next problem, well, actually, I'll take any questions now. Do you have any? Seems pretty easy, right? But that's kind of easy compared to what we'll see later. One other thing, I'm going to make it fun, make it the first 4, just for a second. What would I do if I said the first 4? Well, again, I would need to get my hands on y triple prime. So I'd be taking the derivative of this. How would I take the derivative of y times y prime?
It would be like a product rule.
Product rule. So the derivative of this guy would be 2y times y double prime plus 2y prime times y prime. So they both get a 2. The derivative of y is y prime, and we leave the y prime alone, that gives us this term. This time we leave the y alone, and we take the derivative of y prime, which gives us y double prime. Cool? So if that ever happens, you know what to do. Product rule. Good? Alright. Let's do another. Find the first four non-zero terms for the Taylor series for y double prime minus x cubed. Let's say 2x cubed. Hope this works. Y equals 0. And we know that y of 1 is 2, y prime of 1 is 1. Y of 1 is 2, y prime of 1. Okay, so we want the first four non-zero terms. We already have 2, right? We get these for free, so that's nice. And already our hands on the y double prime, we're just going to plug in 1 for x and 1 for y. Or sorry, let me try that again. We're going to be using this guy right here. So this is y, this is y prime, right? So I'm going to plug in 1 for x. Notice, where's our power series centered here now? 1. So we get y double prime minus 2 times 1 cubed times 2, I should say, equals 0, which means y double prime minus 4 equals 0, means y double prime is 4. Is that agreeable?
Yeah.
Okay. And then as before, we want to take the derivative of both sides because we want to get our hands on y triple prime. The derivative of this would be y triple prime minus, again I'm going to use product rule here, 2x cubed y prime minus 6x squared y equals 0. That's just the product rule between 2x cubed and y. Okay, we're going to plug in what we know. We don't know y triple prime, but we know x is 1. We know y prime is 1. We know x is 1 again, and we know y is 2. So we have y triple prime is equal to, this is minus 2, minus 12 equals 0, so that means y triple prime equals 14. Is that okay? All right, let's construct our series. Y equals, what's our first number in our list? 2. Plus 1 times the next number in my list. But notice it's times x minus 1 because our power series is centered at x equals 1. So the first over 1 factorial plus, next number on our list is 4 times x minus 1 squared over 2 factorial, and lastly plus 14 x minus 1 cubed over 3 factorial, which makes it 2 plus x minus 1 plus 2x minus 1 squared plus 7/3 x minus 1 cubed. Okay. Let's start. So this is pretty easy because we can figure out the first few terms, especially if we're given an initial condition, which these types of problems work really well when you are given an initial condition and you're only told to find the first few terms. But when they don't give you initial conditions, then it gets harder. When they don't tell you to find the first couple terms, they want you to find the general form for the series, then it's much harder. So let's talk about what those would look like. Problem submitted by the audience, we're doing x squared plus 1 times y double prime minus e to the x times y, or e to the x times y prime plus y equals 0. Furthermore, we're told y of 0 equals 1 and y prime of 0 equals 1. What a nightmare. Okay. That's okay. That's actually not going to be too bad. We're looking for the first 4 non-zero terms. All right. Fortunately, we have the first 2, right, by being given these 2 guys. But what we're going to do is we're going to write out, and these are going to be kind of what we use almost all the time for these types of problems, is the summation n equals 0 to infinity, y equals a sub n times x to the n. You could, and this might not be the best way to do this, is you could take this series and plug it in for y, take its derivative, plug it in for y prime, take its derivative again, plug it in here. it gets to be a lot of writing. You're going to have to find that a lot more than what you were doing when you were doing Laplace transforms, unfortunately. And you thought that was a lot of writing. But because, again, it says the first 4 terms only, we might be able to get away by doing this. These are the first 4 terms, right? All we do here is that we pray that none of these are what? 0. Because if they are, then we have to tack on a4x to the 4th. So I think we're good for now. What is y prime? Well, the derivative of this would be a1 plus 2a2x plus 3a3x squared. And then what's the next derivative? That would be 2a2 plus 6a3x. Here's the other weird thing. We don't see them, but they're there. We do have some term. I'm gonna tack this term on. I have a 4a4x cubed, and I have a 12a4x squared. I might need these in a minute because I'm going to need to know what cancels with this x cubed back in y, right? If I didn't put them, I might think that the a3 is the only x cubed term in my series. And for that matter, I'm probably going to put a plus, I have to write it down here, plus 20 a 5x to the third. But we'll see if we need any of that, or all of that, or how much of that, right? Okay, so here we go, ready? X squared plus 1. We know that y double prime is 2a2 plus 6a3x plus 12a4x squared plus 20a5x cubed. Close parentheses. Minus e to the x. Well, e to the x isn't a polynomial, and we can't very well then start grouping in powers on e because, again, e to the x is not a polynomial. However, we can use the fact that, and this is where that old series that I wrote earlier, this is something you wrote down earlier, so I don't say you shouldn't have to write it again, or you can if you want. This is e to the x. Okay? You wrote it down earlier, but we're going to be using that in place of e to the x here. So we're going to be saying, and again, we're only going to use the first 2 terms, 1 plus x squared over 2, and, yeah, plus x cubed over 3 factorial. So instead of saying minus e to the x times y prime, we're going to say minus 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, we're back. Sorry if you missed too much. But in case you missed too much, we're replacing this e to the x here by its power series representation, or at least the first 2 terms of it. So we're listing out 1 plus x squared over 2 plus x, or 2 factorial plus x cubed over 3 factorial, because that's e to the x, or at least a little bit of e to the x. And then this is going to be y prime, which is, according to what we have over here, a1 plus 2a2x plus 3a3x squared plus 4a4x cubed. Cool? And then last but not least, we have a plus y. So we're going to have a plus, only a0 plus a1x plus a2x squared plus a3x cubed. And this is all supposed to equal, when you add it all up, 0. So that plus that equals 0. Huge nightmare. All right. Won't be too bad. Your goal is to group in powers on x. So group in powers on x. Starting with the constant. You tend to start with the smallest, so your CONST and AT8, or just like CONST for constant, that's what I like to do. And you just look at it. I would not recommend expanding this out. Trying to expand this out would be a nightmare. So just kind of glance through and see what's going to produce a constant. Well, if I take x squared and multiply it through by any term here, it's not going to produce a constant, because after all, it has an x in it, right? That's not going to happen. If I take the 1, the only thing I can multiply it by, then this would be the 2a2, and that would produce a constant, right? So I have a 2a2. Over here, we have this next set of parentheses. How can I get a constant here? I can't choose any of these x's, because those are non-constant, and I can't choose any of these x's, because those are non-constant. So the only way I can get a constant out of this is by taking 1 and multiplying it by the a1 here. That gives me minus a1. And lastly, we have a lonely plus a0 over here. These are supposed to sum up in such a way that you get what on the right-hand side? 0. Sometimes the right-hand side, sometimes a non-homogeneous differential equation. What does that mean? Sometimes the right-hand side is what? Something non-zero, right? So you might have an x over here, or an x squared or something. But this is a 0. I don't want you to think it's always going to be 0, because I could very well have put just a straight x over here on the right-hand side, in which case you would set the next, when we do the x to the 1s, we would need this to be 1. We have 1x. If I had 2x, I would need this guy to equal 2. So forth, so on. Okay. There was something I was going to say and I forgot. It was really kind of important. Shit. Multiply it out, multiply it out, multiply. Oh, right. This is what I was going to say. Let's do it. Let's get a different color here. This is a 0. This is a 1. Okay? Now, because we know a1 is 1 and a0 is 1, fuck us. Because, what happens? What's a2 going to be? 0. How frustrating. Because that means we're going to need a plus 30. We'll see. We'll see if we get it. I don't know. We'll see if we get it. But a2 is 0, so that pisses us off. Now we're going to move on to the x terms. How can I get x terms? All right. What are my x terms from this guy? Again, I won't take the x. I won't use the x squared because the x squared is already too big of a power for me to, when I multiply it through any of these, give me just an x. So ignore it. 1 times the 6a3x, will give me 6a3. How about x's over here? There's 2 ways to get x's over here. You could do 1 times 2a2x, or you could do x times, oh shit, went too far, a1. So we get 2a2, or actually, careful here, don't make this mistake, I almost did. I almost said plus, but remember, what do we have on the outside here? We have a minus out in front of this whole thing. So we're going to go minus 2a2 and a minus a1. And then lastly, we have, are we serious? Plus a1. This is ridiculous.
Yeah, these problems are just like a lot of work.
Because now we have a1's cancel. We know a2 is 0. That means a3 is 0. This is something wrong here. Nope, I don't think so. Well, no, I don't think so. Damn, dude. a3 is 0. This is insane. Can we see the answer? That's odd. I at least want to make sure that if we should have a constant term, we should have an x term. According to this, we should not have an x squared term, and we shouldn't have an x cubed term. So I want to make sure that the answer reflects that, because if it doesn't, then I go somewhere we have to figure that out. So 415. Yeah, they do not have an x squared term, and they do not have an x cubed term. So we're doing everything right so far. This just so happened. This is bad. I don't expect it to happen on the test. Yeah, this is really, like, it's one thing for 1-0 to happen. You're like, oh, my day sucked. I stubbed my toe. This is, you stub your toe and then a bird shit on your head. Or there's a dog and you suffer from some withering disease and you're in the hospital and your mom, dad brings in your dog and then your arm falls off and hits your dog on the head and the dog becomes all sad and forlorn and writes sad poetry about what it is in the dog and then a bird shits on your head. So this is what kind of day we're talking about there when we have zeros in a row like that. So we're going to move on to the x squared terms. Great. Let's figure out how we get those. Now, because we're here at the x squared terms, this guy is now a player. This guy's involved. We have an x squared times a 2a2, so we have 2a2. We're going to have a 1 times a 12a4. What about x squareds over here? I'm going to erase this word here. There's again a multitude of ways that we can get x squared out of this guy. We can get the 1 times the 3a3. We can get the x times the 2a2x. And we can get the x squared over 2 factorial times the a1. Cool? So let's write out the multitude of ways that can happen. And again, remember, there's a minus sign here. So minus 3a3 plus 2a2 plus
minus.
Right, minus. Yep, you're right, minus. Minus 2a2 and then minus 1/2 a1. And then, over here, our only x squared term is plus a2. Now, how many x squared terms do I have on the right-hand side here? Way over here on the right-hand side. None. Once again, 0. So I'm going to set this equal to 0. Don't forget, a2 and a3 are both 0, so we can cross them off. a3 is gone, a2 is gone. These are all gone. So I'm left with 2a2, and 2a2 is gone as well. 12a4 minus 1/2 a1. That's nice because I know what a1 is, right? I found these were given to us at the beginning. a1 was given to us to be 1. Because a1 is 1, I can solve for a4, and I'll find that a4 is 1 over 24. Let's construct our power series so far. So we have 1, we just have 1 plus x plus 1 over 24 x to the 4th. Now, why do I know that corresponds to the x to the 4th term? Because look at this power series representation. The x to the 4th power is attached to the a sub 4 term. The x cubed power is attached to the x sub 3 term. So we don't have an x squared, we don't have an x cubed because those terms are both 0, right? But because a sub 4 was 1 over 24, we tack it onto the x to the 4th power. Good? We can do one more, but I want to save you guys time. And I trust that you guys can do it on your own. At this point, you know what we need to do. We're going to have, looking for now the x cubed terms. I'm just going to kind of briefly write it. This guy matches with this guy to make an x cubed. This guy matches with this guy to, no, this guy, whoops. This guy to make an x cubed. Same game with switchboard over here. We're going to have this matches with this matches with this matches with this matches with this, and that's going to give you all your x cubes. And then you have an a3 x cubed over here. Using all the previous values of a0, a1, a2, a3, and a4, we can then find a5. Now, to show you that I'm not just bullshitting you, we can look at what the answer says. Make sure we got at least the first 3 terms right. 15, the solution is 1 plus x plus 1 over 24 times x to the 4th. So we're good there. And as you probably could have guessed, if you were to find a sub 5, you would find it to be 1 over 60 times x to the 5th. Good? Okay. Let's tackle another one, number 19. Ooh, this one's bad. This one's even worse.
Did it ask for 3
First,
terms or 4 terms?
4 terms.
Oh, okay.
Right, which is why I said we're not going to do the last one. I trust you to be able to do it.
Yeah.
The last one in the book tells you 1 over 60. And if you want to do this in the comfort of your own home or you're watching at home and you want to find a sub 5, go nuts. Just I'm not going to do it. It's going to be that, 4 terms from that, and 1 term over there. Do the algebra. Notice how, and again, the big trick here is not to expand anything out. Notice I didn't expand anything out here. That would have taken forever. I'm just going through and kind of scanning for what terms are going to cause me to get an x squared. So I'm going to say, okay, how can I get an x squared from this? I get 1 from here, I get 1 from here, right? Stuff like that, right? Good to keep in mind. Next one. Would you mind reading it to me, actually, number 19? I don't have to keep, switching back and forth.
Okay.
1 second, though.
Yeah.
Okay, I'm ready.
Alright, y double prime minus 2, or e to the 2x, sorry.
You're good?
Y prime plus cosine x y equals 0.
That's
and
it?
then, yeah, and then the initial values, y at 0 is -1, and then y prime at 0 is 1.
Okay. So we have e to the 2x and cosine of x. And again, these are power series that we know. Now, I should tell you that e to the 2x, let's put it this way. We're going to start with e to the x, which is x to the n over n factorial. So what would e to the 2x then be? Well, what I'm going to do is I'm going to replace every instance of x by 2x, right? So then I get 2x to the n over n factorial. And if I write out the first few terms of that, I get 1 plus 2x plus 2x squared plus 4/3 x cubed. Let me talk about why briefly, how that happens. I'm going to replace every instance of x by 2x, so that x becomes 2x. Replace that x by 2x. When I square 2x, it becomes 4x squared, but divided by 2 gives me 2. 2, when I cube it, gives me 8. 8 divided by 3 factorial. 3 factorial is 6. 8 divided by 6 is 4/3. Cool. I just want to bring to everyone's attention that in 10 days, less than that, I turn 10,000 days old.
That's pretty cool.
The big 10000. People ask me, how old is that? How old are you then? I'm like, 9,992 days old. How old are you? They want to know it in years, of course. I say, just grab your fucking iPhone or do the long division. That's what I did. Anyway, just so you know, fun day. And you too can figure out, if you do the division, can figure out how old I am and then how old you'll be roughly when you turn 10,000 days. And have a big fucking party for it like I'm going to do. All right. Now, what was I saying? Back to this. This is e to the x, that's this guy. Replace every instance of x by 2x to get that. And then cosine of x is also decided rear its ugly head, but I'll write out the first few terms of it. The nice thing is, the terms in cosine skip are only the even powers of x. So we even though we wrote 3 terms for e to the 2x, we don't need to write that many. We wrote 4 terms for e to the x. We don't need to write 4 for this guy because it goes x to the 4th. It's already way too big. We probably won't use this guy. Keep that in mind. Okay, y double prime. Just copying what we did from last time. That's 2a2. I really should have erased it over there, so my bad. If you want to reference the second derivative from the last problem, it's just 2a2 plus 6a3x plus 12a4x squared plus that we might be good there. Let's just pretend. Let's just hope we're going to be good there. I'll leave some space. Minus e to the 2x is 1 plus 2x plus 2x squared plus 4/3 x cubed times y prime. And again, you can reference the previous page. And by the way, I recommend not only memorizing this and the first with those when you listen out, but you're probably just going to be doing this so often that you're going to have this memorized. And you're going to have this memorized. A1 plus 2a2. I see. You don't have it memorized, but not like me. 2a2x plus 3a3x squared plus 4a4x cubed. Start. Just make sure it doesn't break. Okay. And then lastly, we have plus cosine of x times y. Cosine of x is this 1 minus x squared over 2 factorial. And you know what? We're just probably not even going to use the x to the 4th term. It's just not going to get that big. So I'm just going to say 1 minus x squared over 2 factorial. That's fine, or over 2. Because the x to the 4th is just going to be too high a power that we're probably not going to use it. Unless we get a string of zeros that we need it, but I don't think we will. And then this guy, a0 plus a1 plus, or a1x plus a2 x squared plus a3 x cubed. I think that's good enough. And again, this all equals 0. All right. Let's group and powers on x. Start with the constant C1 ST. What constants do we have?
2,
Got a 2a2. What else?
A1.
Minus a1.
A minus a1. Be careful. Once again, this minus is here. This guy's a dick. Minus a1. And then we have what over here?
Plus a naught.
Plus a naught. Yep, I agree. And it's supposed to equal 0. Good. Now, we know that, and again, don't forget this, these are a0 and a1. We're going to plug in this for a naught and plug that in for a1 to give us a2 equals 1. If you plug in negative 1 for a naught, plug in 1 for a1, you get 2a2 minus 1 minus 1, which is minus 2. Add the 2 over divided by 2, so you get a2 equals 1. Nice. All right, now we're going to go to the x to the 1 term. X to the 1 term. How many x's can we get here for this first guy?
1.
6a3 of them, right? How many x's can I get from over here? There's 2 ways to get them.
There's minus 2a2.
There's a minus 2a2 and a what?
Minus 2a1.
And a minus 2a1. So minus 2a2 and minus 2a1. And for those of you watching at home in confusion, we can take this 1 and pair it with this 2a, 2x, and take this 2x and pair it with this a1. Good? And then lastly, we have 1 times a1, so we're going to have a plus a1. There's no way to get any other x's. Cool? So we're going to plug in all everything we know here. We know actually a1 and a2 are all 1, so we have minus 2 is minus 4, plus 1 is minus 3, so we have 6a3 minus 3 equals 0, which means a3 equals 1/2. What's our power series then? Well, our first term, well, I'll let you guys write that down first, because I don't want to make the big reveal that you guys getting caught up.
And this power series is always going to be in the structure of
This guy?
a sub n
Times x to the n. That's right. Unless it's centered somewhere else. If it's centered somewhere else, you might see something like minus 1 squared, or to the n rather, I should say. Okay. Keep that in mind. But I don't want to keep that go away. Okay. There is a type of problem that I may not cover today, but I want to, possibly, where everything gets shifted, like a y of 1 sort of thing. If, like, we'll see. I'll ask you guys if you've seen such a problem. But it's kind of difficult. Even I have to rethink through it for a bit. Anyway, yeah, this is what the show always look like, unless it's centered at something else. If it's centered at 0, which 95% of them are, is what you're dealing with. Okay. What's our A1? What's our A0? -1. A1 is 1, so we have plus 1x. Our A2 was 1, so we have plus x squared. And our A3 term was 1/2, so we have plus 1/2 x cubed. And this is the first 3 non-zero terms of the power series representation to the solution of that differential equation. Now, could you start writing out, could you go way down the line and figure out what A4 and A5 and A6 and A7, you could figure out what those are. Is it likely that they would produce a power series that you would recognize? Probably not. I mean, look at this differential equation. It is such that I take its second derivative, I take its first derivative multiplied by e to the 2x, and I take the original function multiplied by cosine. I can't think of what function would satisfy this sort of crazy differential equation. There will be times where you can, not always, it depends on how keen your eye is, but sometimes you can say, oh look, I noticed, you might see, you might start writing up the first 4 terms of a non-zero terms of a Taylor series that represents your solution, and you start getting this, right? At which point you would think, holy shit, my solution is what? The solution to the differential equation is what?
e to the x.
Right? If you do the work for y prime minus y equals 0, what does y prime minus y equals 0 give you? What's the solution to that? Right. E to the x is its own derivative, right? It's like that whole poem, My Own Grandfather or whatever. E to the x, you're looking at me.
Yeah.
You've heard of it, okay. The derivative of e to the x is e to the x, and subtract e to the x gives you 0, right? And if you do the work, and it's not going to be nearly as bad as this, what I have here, but it will just be this plus, or minus this. And if you're solving for coefficients, you end up finding that, oh, look what I end up getting. I get 1, and I get 1x, and I get x squared over 2, and I get x cubed over 6, and so on. And you're like, oh, no shit. My solution to this differential equation is e to the x. So I shouldn't be surprised that when I start constructing the power series solution for it, I get the power series representation for e to the x. Cool? But again, this is not one, I mean, I could write out 20 more terms and think, I have no fucking idea what that is, because it's just so wacky crazy. And I'm going to check to make sure our answer's right. 8, 4. This is number 19. 8, 4, number 19. -1 plus x squared plus 1/2 x cubed. Yep, cool, good. All right, we did those two.
So this can be used in place of doing what you said earlier, where you
take the derivative.
Say y is equal to that summation, and then take the derivative of that, and the derivative of that. And then.
The reason that that's not quite, actually, maybe you're right. I wonder if that's what I should have been doing all along, actually, now I think about it. Shit. Probably really embarrassing. Maybe that's what I could have been doing the entire time. Oh, shit. Yeah, I probably could have just done that. Wow, that's really sad. I made this really much more complicated than it had to be, but there will be times when this is necessary. This is a necessary step. Mm-hmm. That's usually when I'm not given these. Okay, I'll tell you what to do in that case. But I think you're right. I could have actually just done that. I feel really stupid now. Let's see, if I plug in 0 for x, I plug in -1 for y, I get y double prime minus 1 plus 1, right, and then that would work, minus 1, yeah. Now, for that, with that in mind, I would have gotten y double prime equals 2. That doesn't mean a sub 2 is 2. Remember, you have to, it's the second number on my list, so what I do is say 2 times x minus 0 to the second power over 2 factorial, and that would have given you 1. So yeah, I kind of did this in a very roundabout way, but there will be times where this is a necessary process. And so while it was very long, drawn out, roundabout, like I could have just done it the way I did the last few problems. So I just gave you good practice with the long way, in which case something like that will happen. But yes, to answer your question, I absolutely could have. Now, what would I have had to do to get my x cubed term? I would have had to take the derivative of this. Not that bad. I would have had to do product rule here and a product rule here. Still not that bad compared to collecting all this shit like that, you know?
Yeah.
I would much rather do 2 product rules than deal with all this mess. Cool? But yeah, the way we did the last 2 problems, or the previous 2 problems before we started these 2 problems, could have been used here. There will be times where that method won't work. This is not one of those times apparently, but still good practice for what we'll see to come. Do you know what's next besides these 2 problems?
I have one for nature 5.
Okay, 5? This one?
Yeah.
Oh, this is weird. Oh, this is, okay. These are great. It's weird because these aren't that bad, and I don't know why they're in here because they don't require a series, any sort of power series to do. But they have application in Frobenius theorem. These examples aren't that bad. They make me happy. I'll talk a little bit about why. Let's think about the first time we saw a differential equation like this. I'm making this up right now. Don't write it down. It could never have been the case that this was the solution of this was a polynomial. This would never have been anything of the form a n x to the n plus a sub n minus 1 x to the n minus 1 plus dot dot plus a1x plus a naught. This would never have happened. So this is a polynomial. A polynomial would never have been a solution to this, and here's why. What degree is this polynomial? N, right? So if this term is 0, which we're assuming it's not, otherwise we wouldn't have written it, there will be an an x to the n term here, sitting ready to be canceled because after all, how many x to the n terms occur on the right? None. But what degree is y prime?
First.
N minus 1, not the first. No, yeah, by degree I mean like not first order or anything like that. By degree I mean the degree of the polynomial. So if y is given by this, the y prime, the derivative of that, will decrease the degree of that by 1, right? If you've got a degree 3 polynomial, you take its derivative, you get a degree 2 polynomial. So this would be a degree, this would be n times an x to the n minus 1. Whatever the case is, we have a degree n minus 1 here. And if you take another derivative, the degree will be lower still. So the point is, what will ever cancel that x to the n? The answer is nothing. Nothing will cancel it. And so a polynomial can never be a solution to this. And you know the solution is this ends up being, if it was a minus here, it would be e to the 4x, c1 e to the 4x plus c2 e to the negative x, right? Based on the auxiliary equation factoring whatnot. What happens, though, when you introduce some x's? What happens when I have something like x squared? And I put an x here. You probably have seen these before. These are called equidimensional equations or Cauchy-Euler equations. Have you seen them before? Mm-hmm. You're seeing them again here, which is kind of weird because I think you see them in section 4 something or 5 something. So it's weird they're cropping up again. I don't know. I honestly don't know why they're cropping up again. I think because it has something to do with the method of Frobenius. But it will look very familiar to things we've done in the past. The cool thing about the way this works is this is degree n, right? What is y prime? As we said before, degree n minus 1. But because we have this extra factor of x, it reconstitutes the power of n that we had before. Same with this guy. This is degree n minus 2, but having the presence of the x squared reconstitutes the power and brings it back up to n. So everything's a nice degree, and that makes me really happy. I don't know why, but it makes me feel warm and fuzzy inside. So let's tackle the problem you wanted to do. X cubed y triple prime. 4x squared, 10x, negative 10. And it says use the substitution y equals x to the r. in general, you always use this substitution whenever you're dealing with an equidimensional equation. Whenever you're dealing with a differential equation where x is being multiplied by the x to the n is being multiplied by the nth derivative. So x to the first is being multiplied by the first derivative, x to the second is being multiplied by the second derivative, x to the third is being multiplied by the third derivative. You always make this substitution. Now there's actually an auxiliary equation for the two-dimensional one, whatever, but you don't memorize it, just plug it in and solve. So watch carefully, I'm going to plug x to the r into each of these. I'll get x cubed times all I do is take the first, second, and third derivatives of this guy. At this point, you can almost just ignore the fact that there's an x cubed in front, because we know that this x cubed, well, watch carefully, this x cubed will cause that minus 3 to go away. And this x squared will cause that minus 2 to go away. And this x will cause that negative 1 to go away. In such a way that every term now has a what? A simple x to the r, right? Which I will now factor out and be left with, here we go, buckle up, r cubed minus 3r squared plus 2r plus 4r squared minus 4 plus 10r minus 10. Just expanded that. 4 times r minus 1 would be 4r squared minus 4r. Right there, minus 4r. Good? Okay, now we're going to, we have two factors. There's a multiplication. There's this times this, and it's supposed to equal 0. The only way that can happen is if this is 0, or if this is 0. Well, how can that be 0? It can be only when x is 0, right? But that's not a general solution. A solution to a differential equation is a function, not the number x equals 0. So, only this can equal 0. We're going to factor that in a minute. What we're going to do is, I'm going to rewrite it up above here. R cubed, we've got a minus 3r squared and a plus 4r squared, so we've got plus r squared. We've got a plus 2r, a minus 4r, and a plus 10r, so that would be plus 8r, I believe. And then we have a minus 10 equals 0. For what values of x is, or for what values of r, I should say, is r cubed plus r squared plus 8r minus 10 equals 0. Well, this is where you're going to have to break out some synthetic division, because when's the last time you guys factored a cubic polynomial? Been a while? Been about a minute? What you can always do is check some small numbers, some good guesses. What's a good attempt to try and solve that one? What's a really good number to plug in and check see if it's right? 1. Sure enough. 1 plus 1 plus 8 is 10, minus 10 is 0. They're going to tend to do that. Try 0. Well, 0 will only be obviously if every term had an r in it, but because there's a constant here, 0 is obviously not going to work. If you try 1, then you try negative 1, then you try 2, you try negative 2. Stuff like that. So we try and try 1, and sure enough, 1 plus 1 plus 8 minus 10 equals 0, so check. So we know that r equals 1 is the solution to this, and we're going to factor it out by using synthetic division. So here's what I'm going to do. You draw this little box like this little box here, this little line. You put the number that is the root, which we found bx equals, or r equals 1, here in that box. And then you list the coefficients of the polynomial in descending order. So I should say in descending degree order. 1, 1, 8, negative 10. 1, 1, 8, negative 10. So the first thing you do is you pull the 1 down. The 1 always comes down. This row, whatever it is. And by the way, I don't mean this one. I mean whatever the first coefficient is in your list. It always comes down. So we're going to plot it right there. 1 times 1 is 1. We're going to put it there. And we add. You can put a plus sign there if you want to remind yourself you're going to be adding these. So we get 1 times 1 is 1, plot it there. 1 plus 1 is 2. 1 times 2 is 2, plot it there. Add it to the 8 that's already there. 8 plus 2 is 10. 1 times 10 is 10. And what should happen is these cancel and give you 0. If it doesn't give you 0, r equals 1 was not a factor in the first place, or wasn't a solution in the first place. There should be, what this means is there's no remainder. So then we're left with, so here's how this factors, this r cubed times, or plus r squared plus 8r minus 10, it factors into r minus 1. Why r minus 1? What was the corresponding root? The root was 1, right? So there should be a factor of r minus 1. And then what's the remaining polynomial? It's called a depressed polynomial. Need some Zoloff. R squared plus 2r plus 10. Kind of a pain in the ass because this doesn't factor, but I do recognize this as the quadratic equation which has negative 1 plus or minus 3i as its roots. Right? You can just see that, right? If you want to complete the square, so this becomes r plus 1 squared plus 9. Have you guys just is that how you do that? Is that you're familiar with that? I just did r squared plus 2r. I know this is not going to factor, so I would say r squared plus 2r is really r plus 1 squared. And then what's 1 squared?
1.
Subtract it from the 9 to get, subtract from the 10 to get 9, right? We set that equal to 0 and solve for r. We get r plus 1 squared equals negative 9, which means r plus 1 equals plus or minus 3i, which means r equals negative 1 plus or minus 3i. Good? Okay. So we found our roots. R equals 1, r equals 1, negative 1 plus 3i, and negative 1 minus 3i. We gotta figure out what that means for our solutions. This is where things get weird. So let's say this. R equals 1, negative 1 plus 3i, plus minus 3i. What does it mean for our solutions? You might be tempted to say y equals c1 times, remember, what was our substitution way at the very beginning? Y equals x to the r, right? This is the big kahuna here. We found the values of r. We found that r equals 1, so we have c1 times x to the 1. This actually works out pretty well if you go back to the differential equation. Look at the differential equation for a moment. That's the beauty of these is that they kind of work out really well. You can check pretty easily if they are indeed a solution. So I put an x there, I get negative 10x. What's the first derivative of x? 1. So I get 10x. I get 10x minus 10x, which is 0. What's the second derivative of x?
0.
0 was the third derivative of x.
0.
So these go away. You just had 10x minus 10x, which is 0. So hey, it checked out. It worked out. But what about this complex number 1? And then, so again, you can check your answer pretty quickly by taking a couple derivatives and plugging it in, if you so please. What about this guy? What do we do here? Plus c2x to the negative 1 plus 3i. What the hell is going on here, right? Well, when this happens, here's what you do. If r equals negative 1 plus or minus 3i, gotta make sure I've got this correct. I should say a plus or minus bi. Then you're going to have, here we go, x to the a times c1 cosine of ln of x plus c2 sine of ln of x. Buckle up. Yeah. Make sure that's right. Yeah. No. Need a b. Let's make that a beta. Make this an alpha. So, because our roots were negative, our extra roots were negative 1 plus or minus 3i, we're going to have plus x to the negative 1 times c2. I know it says c1 here, but that's because I'm assuming there's no other constant. So c1's already been used up. We're going to move on to c2. Cosine of 3 ln x plus c3 sine of 3 ln x. There's the negative 1. There's the 3. Have you done these Cauchy-Euler questions before? No? Have you?
Yeah, we went over it briefly in class.
But recently, not like weeks ago or like months ago? No?
Not like this, no.
Okay. Okay. Before I do Frobenius, I kind of want to do some other solution to differential equations. But
can you talk about free, like what makes base of n free or not? Do you know what that means?
By that, I'm guessing he means.
He means like it could be anything,
right.
But like sometimes like.
So what that means is when we're doing those types of problems, we're not given those initial conditions. Like we're not told y of 0 equals 1 or y prime of 0 equals 2. That's what I'm assuming he means. So what that means is your answer will have a0s and a1s in the solution.
Okay.
Let's look up some examples.
Okay, let me see what we did.
Yeah, actually, I'm just gonna go to my problems.
Is that just one you just can't solve?
Right. So I think we're gonna try one. Hopefully, this doesn't turn out too badly. So we're gonna do one where we have free variables. I guess is what he calls them, or what?
Yeah, he just says they're free. I don't really know. Because they're not necessarily constants, or they have to be constants, right?
They're all constants. You just don't know what they are.
Okay.
And it's because it kind of is. It's like the C1 and C2. Okay. All right. So let's say solve y prime minus 2xy equals 0. Okay. What we're not given, we want a power series solution. But we're not given anything like a sub 0 is 1 or anything like that. So we have you say that y of 0 equals a naught. Kind of what you're working with, okay? So we're gonna do our usual y prime according to our power series. Let's go with black. a1 plus 2a2x plus 3a3x cubed plus 4a4x to the so this is squared here, cubed. Let's say that stop there. Of course, it's ... minus 2x times a0 plus a1 plus a1x plus a2x squared plus a3x cubed plus ... This is where we're probably going to have to find a pattern. We're not asking for the first 4 terms. If I say find a power series solution, I want the whole thing. I want your answer better damn well be summation of, and I should have a formula here, times x to the n. So this might be n factorial over 2, or it could be 3 to the n over n factorial. It could be lots of different things. It could be all straight. We don't know. We're going to figure out the pattern based on what we see from these coefficients, all right? So starting with, again, our usual method is group. Group in powers on x. C1 ST. We have a1, and we have a minus 2x a0. Well, shit. What happens now? No, we don't have a 2x a0, right? There will be no constants that come out of this, right? There is a constant here, a0, but multiplied by a 2x doesn't become a constant anymore. We just have a regular old a1, right? What does that mean for our value of x? Or what does that mean for this value of a1? What must it be?
0.
There's no other terms, and it's not going to be related to any other term, so it's done. That's it. The only constant term we get is a1, and since s equals 0 on the very end over there, it's got to be 0. Cool?
Do we just assume that this is centered at 0?
Yes, we tend to assume this is centered at 0. Let's move to the x term. We have a 2a2, and we have a minus 2a0. Okay? From here, we can find out that just means a2 equals a0. Okay? That's still not enough information to do anything with that just yet. That's too little information to figure out a pattern. Move to x squared. X squared terms, we have 3a3 minus 2a1 equals 0. What do we know about a1?
0.
It's 0, so a3 is going to end up being 0. X cubed terms, we've got 4a4, we're going to have minus 2a2 equals 0, which means we have a4 equals 1/2 a2. But we tend to want to have these things strictly in terms of a0. So since a2 is a0, this is really 1/2 a0. I'm going to be taking up the whole bottom half of this board by doing these patterns, so bear with me. See if it's still on the... I hope my video hasn't stopped. Please God. Okay, recording still is. Can I see everything? Yes, okay. The x to the 4th terms now. Well, guess what? X to the 4th has got, where the hell am I? X to the 4th. There's going to be a 5a5. We don't see it, but it's there. A 5a5, and we have a minus 2a3. What do we know about a3?
It's 0.
It's 0. a3 is 0, so guess what? a5 is 0. And you probably had to guess, what do you think a7 would be?
0.
And a9?
0.
And all these odd terms, so a sub 2n plus 1 is going to be 0. Okay? So we can kind of skip those. We're going to go to x to the 5th term. Again, we don't see it, but it is there. It would be 6a6 minus, there would be a4 x to the 4 here. So multiply by the negative 2x here, we get minus 2a4 equals 0, which means a6 is 1/3 a sub 4. But what is a sub 4 in terms of a sub 0?
1/2 a sub 0.
1/2 a sub 0. So we're replacing that a sub 4 by, again, it's right here, there's a sub 4 is there. We're going to take this guy, bring him over here, and this is really 1/6 a sub 0. Okay? Let's skip a sub 6, or rather skip a sub 7. We're going to go straight to x to the 7th. It's going to be 8 a sub 8 minus 2 a sub 6, which says that a sub 8 is 1/4 a sub 6. But again, a sub 6 is 1/6 a naught, so this would be 1/24. 1/6 times 1/4 would be 1/24 a sub 0. At that point, I'm going to stop and say we can figure out a pattern now. So we've got a0, the one boxes up, a0, a2 is a0. Let's start here. We got a0, 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 1/2 a0, 1/6 a0, 1/24 a0. Does anyone recognize these coefficients?
It's factorial.
It is factorial, right? 1, 1, 1/2, 1/6, 1/24. Those are 1 over in factorial. So our pattern there is, we've kind of got our pattern there. Let's write up. Let's do it in blue. We've got a0 plus, or I'll start with this way. Let's say a0 plus a1 plus x plus a2 x squared plus a3 x cubed plus a4 x to the 4th plus dot dot. What do we know about a1? 0, right? What about a3? 0. Let's stop and start. A5 also 0. We know a2 is equal to a0. And we know a4 is equal to 1/2 a0. And this would be x to the 4th, right? And we know the a6 x to the 6th would be 1/6 a0 x to the 6th. Then we know the a sub 8 term would be 1/24 a sub 0 x to the 8th. Okay? So what's the pattern here? What kind of powers do we get on x? Even powers, I agree. So we're going to have summation n equals, this is the big final answer. We're going to get there. We have even power, so x to the 2n. What do we have on the bottom? 2, 6, 24, those are the what? Factorials. I think that's about it. The only thing that I don't have here in my answer that is up there is what? What does every term up there have? A sub 0. So very often you see a sub 0 times that entire thing, like that.
So a sub 0 is for either.
Yes,
because
right,
we've never
right.
solved for it.
Exactly. and it wasn't given. So you see how we did that stuff earlier, and I said you really could have just done the method we did for the first two problems and just taken some derivatives and plugged in numbers. That won't work here because I don't have any numbers. I don't know what y of 0 is. Make sense? Cool.
Is that?
Maybe it would. Right? What's up?
No.
Not quite, though. Well, kind of. But then you have to do it. I'm going to stick with this way. Okay. Now, what we're going to say is that what?
To say that is that cosine, but it's not.
It's close. What we are going to do is we're going to solve this the normal way and show you that this is very similar to a power series. You know, actually, this without the 2. Do I want to say anything? Do I spoil it? Yes, I do. Without the 2, what power series is this? E to the x, right? What must have been replaced? What must have x been replaced by in such a way to get x to the 2 in? What would you replace x by?
Oh, e to the x squared.
Right, e to the x squared, right? So this would have been, this must be, as you said, e to the x squared, right? Because I must have replaced, in order to get a 2 up there, I must have replaced x by x squared, and x squared then to the end is x to the 2 in. So this guy is e to the x squared. Cool? Let's solve this the old-fashioned way, though. This is where things get really attractive. Watch. This is a separable differential equation. I know it's been a while since you've seen that. I'm going to add this over to both sides, so we get y prime equals 2xy, right? It's separable, so I'm going to divide both sides by y, leave the, and I'm going to write this as dy dx. You don't have to do this, but it is kind of cool. You just watch. Divide both sides by divide both sides by y, and multiply both sides by dx to get dy over y equals 2x dx. At that point, because we have a function of y on the left and a function of x on the right, what do we do to both sides? Integrate. What's the integral of dy over y? Natural log of y, good. Integral of 2x dx is x squared plus c. We're almost done. What do you do to both sides to get y? Exponentiate both sides, wonderful. And you get y equals, what happens with e to the x squared plus c? What happens to that plus c?
C or k.
It's like k, right? It comes down in front. C times e to the x squared. Well, what is this?
That's so much easier.
Court. Well, that's not the way they want you to do it, though. And not always will be the case that it's going to be some sort of separable differential equation, but that's kind of how that works out. We'll do one more like this. Where the pattern's a bit harder to find. Actually, a lot harder. I canceled. Damn, dude. Sorry.
So the even powers were giving me 0, though.
It's kind of odd, right? That the even powers are giving me 0. That really has no bearing on
the final summation.
Right.
Okay.
Mm-hmm. Let's do. Yeah.
You already raised it. But how did you know that was x to the 2n, though?
What kind of powers did we see? I gotcha. I see what you're saying. Well, a sub 8 was 1 over 24 a0, right?
Yes.
That means the coefficient of the x to the 8th term. Because remember, the power series is of this form, right?
Okay.
So if I know a sub 8 is 1 over 24 a sub 0, I know this guy's 1 over 24 a sub 0 times x to a power. It's got to be 8, because it matches that.
Okay.
Okay, we're going to do this one more. Sure, I hope this works. I have no idea if this is going to work. But I think I wrote this problem a while ago, and it broke. And I just threw my hands in disgust. But here we go. That might happen here. Oh, God, I really hope it doesn't happen here. I have a weird premonition about this guy. Okay. Here, the ones that are free, are A1 and A0. We don't know either of those. And the reason is that, think of it this way. You know how a second order differential equation has a C1 and a C2? Mm-hmm. That A1 and A0 are like your C1 and C2. So you should expect, it very often is the case that you expect your solution to be something like A0 times one series plus A1 times another series.
And that's just because of the degree.
Because of the order of the differential equation, exactly, right? Just much the same way when we did any other second order differential equation, we had a C1 and a C2. We expect to have an A1 and an A0 and an A1. I hope to God this works out really well. Here we go, though. Let's see if this works. So y of 0 is a 0, and y prime 0 is a 1. We're going to go ahead and put our first, this is just not going to work. I know it's not going to work. It's a good nightmare. I did divided by x. That won't work because it's not. I might change it to be x. We'll see. 2a1 plus 6a3x plus 12a4x squared plus 20a5x cubed plus 30a6x to the fourth. We might not need that many, but it's just nice having a lot of terms so that we know we can work with those. So minus x times a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth. Okay, this is all equals 0. Here we go. I'm going to hope this works. I just remember thinking I did this problem before and everything came out to be 0. Every single number came out to be 0. Because that would be a solution though. Shit. Right? Yeah. 0 would be a solution. That's boring. That's okay, I guess.
Is it because we like started 8.6 very briefly, and like he showed us a problem early in the week and said that we could only find one of the two, and then he's like, "Oh, you need to use something else to find."
That's Frobenius. That's Frobenius. I think.
Okay.
But you know what's going to happen here is that one of the solutions is just y equals 0. That's going to happen. That's going to be okay, I think. So after all, why would I plug in 0 here? Oh no, that's just always going to be a solution. Shit, that can't be right then. Never mind. I don't know. I'm just an idiot. All right, we're going to figure out this. We're going to figure out. Let's start with the group. We're going to group, right? Constants. C1 ST. I hope this works. We got a 2a1. And we have none over there. Oh shit. See, this is already fucking weird. Let's change it a little bit. I'm going to change it just a little bit. Watch carefully. I'm going to put the x here. I'm going to get rid of it over here. Nope, that barely helps at all. Fuck me. Maybe. We'll see. I don't know. Well, the constant in this case would be a0, which means equals 0, which means a0 is 0. Okay, that's fine. How about the x to the 1 terms? All right, these got works. Okay. This would be 2. By the way, this would be 2a2.
2a2?
What the hell is going on? Yeah, 2a2. Yeah. Okay, much better. Okay. The x to the 1 terms. We have 2a2 of them here. And we have minus a1 of them over here. So we have a1, or rather I should say a2 equals 1/2 a1. I hope. How about the x squared terms? Okay, x squared. We have a 6a3 and a minus a1. Oh, a2. Yes, I'm losing my mind right now. I'm sorry. Minus a2. Well, we know this tells us that a3 is 1/6 a2, but a2 is 1/2 a1. So we have 1/12 a1. X cubed. We have a 12a4 and a minus a3, which tells us a4 is equal to 1/12 a3. But we know a3 is 1/12 a1, so we get 1 over 144 a1. At this point, you might think, I got a lot of numbers here. How can I not figure out a pattern just yet? And sometimes you're going to be like really frustrated. What is the pattern here? You could try this. Let's have a look. What am I multiplying this 2 by to get 12? 6. So I'm multiplying this in the bottom by 6. What am I multiplying 12 by to get 144? 12. My guess is that we're going to be multiplying by 18 next, but we'll see. Let's look at x to the 4th. Just a guess. I have no fucking clue, actually. It's probably wrong. X to the 4th terms. We have a 30. No, we have a 20, a5. Minus, and we have a a4, minus a4. So that means a4 is equal to or a5, I should say, is 1/20th a4. But since a4 is 1 over 144, we have 1 over 2880. So I multiply this by 20. It's hard to see what the pattern is here. It's definitely really difficult. So here's what we're going to do. 1/2, 1/6, or actually 1/12. 1 over 144, 1 over 2880. This was multiplied by 6. This was multiplied by 12. This was multiplied by 20. I can tell you, do you see these numbers anywhere else?
The constant.
Yeah, the constant coefficients over here. In fact, you could even say you started with a 1, and the a1 became 1/2, right? So it started as a 1, and you multiply this by a 2 in the denominator. 2, 6, 12, 20. 2, 6, 12, 20. If you had to guess, the next coefficient would be 1/30th, whatever that is, right? Pattern's kind of hard to see there, with that in mind. What is this pattern? What is the closed form of this pattern? Oh, shit. It is... I have no fucking idea. This is where I have to get Sloan's out. I could sit and think about it, but I'm going to use the online encyclopedia of integers. So 2, 12, 144, 2880, and it's going to give me 1. N factorial times n plus 1 factorial. Huh. So you see, this is probably not going to happen to you. But that's what these are. What's 1 factorial times 1 plus 1 factorial? What's 1 factorial is 1 times 2 is 2, right? What is 2 factorial times 3 factorial? That's not quite right. Oh, yeah, these numbers, though. We're looking at these numbers. 12 is 2 factorial times 3 factorial. 2 factorial is 2, 3 factorial is 6. 2 times 6 is 12. 3 factorial times 4 factorial would be
6 times 24.
is 144.
Okay.
Now, how could you figure this out without, again, using Sloan's? By the way,
Did you just leave it like that and multiply it by the constant at the beginning? Is he like, I mean, how did you come up with
Yeah, I think so. I don't know if Bona or whoever your professor is would ever expect you to. So here, first I'm going to do this. Because we found the constant a sub 0 is 0, we could have y equals a sub 0. You could say that's 0 or something. I don't know. Plus a1 times a1 is the coefficient of which term in your power series? A1 is the coefficient of x to the... Yeah, a1 is the coefficient of x to the 1. So we have x plus. Then a sub 2 is the coefficient of the x squared term, but it's half of what it is for a1. And since the coefficient for a1 is 1, or just a1, we're going to have half that. Then we have a 12th of that. 1/44th of that. That's your power series representation. Could you write it in a summation like you could write it like this? I don't know. Again, I don't know if you'll lose credit for this or anything. So I want to start with n equals 1 here. Over n factorial times n plus 1 factorial. How could you have figured these numbers out on their own? That's really advanced pattern finding at that point. You got to realize that if you solve these numbers 2, 6, 12, 20, these were the previous powers of x squared. This what used to be an x squared, right? So a 2 came down and a 1 came down, so it became 2 times a 1, right? Here we had a 3 come down and a 2 come down, so it was a 3 times a 2. We had a 4 times a 2 come down, or a 4 times a 3. This had a 5 and a 4, and this was a 6 and a 5. But remember, in every step when you solve for the next one, you were multiplying by the ones that were already there from the past. So that is, when you went to go find a sub 4, you picked up a 4, a 3, and a 2. That's a factorial. You also picked up a 3, a 2, and a 1, which is the other factorial. Does that make sense? Mm-hmm. It's really hard to see that's what was going on, but and again, I don't think the pattern would be ever be that hard for you to find. So not something insane like this, but that's what the answer to this differential equation is. Cool? Okay, with that in mind, I'm going to stop there and ask you guys if you have any questions about this or any other type of problem that you've seen in class. So I'll take a question from you if you have one, or if you just want to see more of the same of what I'm doing, we can do that. If you've got method of Frobenius, we can do that too, because that's kind of like the very last thing we need to do for you. But I don't know if you're going to get to it. You might not.
Do your tests coming up as well? Or?
We just started this week. I guess, are you guys done after this next test?
No, we have a 2-part final on the last 2 days of class. Then it's it's
How about you're done learning? Or done doing new material?
Yeah, there's nothing new, right? After series, there's nothing new.
Yeah, I don't know. He hasn't said. So
No,
he
the
doesn't
series should
really
be
want
cool.
to say.
Series should be it. It's just funny that you got in there this quickly. Well, let's
But he
see.
said he wants to spend a lot of time on it, so I'm sure.
Okay, let's look at the test then that you had on your phone.
Okay.
Unless you had a question. But again, you probably don't know what to ask, I guess, since you're kind of fresh to it.
Yeah, but one of the things he did in class, he was doing homogeneous linear equation. He put it in a standard form, and then he would, kind of like what we were doing, he would set it up as a summation, and then he would leave it in that when he did the derivative.
Yes, right. So instead of writing the things out like I was doing,
but it's like the same, like
it is the same
thing.
It's the same.
Okay.
Now it gets it's more concise. For instance, let's say we were doing that. It's hard to do. Let's suppose for a moment, let's say plus x y prime minus, let's say 2x y prime minus 4y. I guess I don't know. Let's just leave that as minus y. Sure, make it like that. Okay. To tackle this type of problem, he would have had summation n equals, this is a good one, and then I'll take your question next, or the one on your phone. This is kind of a pain in the ass. Okay, so we're going to revisit that. Y equals summation a n x to the n, starting with n equals 0 to infinity. When we take the first derivative, we get n a sub n x to the n minus 1. Something worth noting is, this is something you remember doing back in Calc 2, what's the, you can move this up one. What's the, when I plug in 0 here, what do I get? 0 for n. I get what? 0. 0. That makes sense because the first term spit out of this series is what? A0, which is just a,
right.
Just a what?
Just
Constant. Which when you take its derivative gives you what?
0.
0. That's what's going on here. Remember, we have a0 plus a1x plus a2x squared. The only thing that won't go, the only thing that will go away when you take its derivative is the a0 because it's a constant. So this term will vanish, and you won't see it here. So with that in mind, you don't need to start with n equals 0, you start with n equals 1. Okay? Same thing when you go to the next derivative, you start with n equals 2 because you're going to have an n times an n minus 1, a sub n to the x, or a sub n times x to the n minus 2. Okay? And again, now the a1x term that was here, when you take two derivatives of it, will also go away. So here's the thing. I'm going to put those here in this summation as follows. Now, as far as the method you're supposed to use, I don't think it matters what method you use. Some people prefer this method because it's really short and concise, and I'm not having to go looking around for all the different terms and collecting and grouping like that. But it makes me happier to write it all out, see it all there, and I don't feel like I'm missing anything. But, it depends what you want to do. If you like this, it's short and concise. There's a little bit of bookkeeping you've got to do here, just as there was for the other one, because you're going to, what do we do when we got to this kind of write everything out? What was the next step? It was group and powers of x, right? The problem is we can't group here because all the powers of x are different. In fact, even more different because of this x here. So we're going to move this guy into there. So that x got moved into the inside of the summation because it doesn't depend on n, right? So that x got absorbed by that x to the n minus 1, making it an x to the n. And then what we're going to do is, we want all the powers to be the same. So here we go. What I'm going to do is, this is what's called changing the index. So I want the power up here to be an n, just like all these. So what I'm going to do is I'm going to bump this up by 2. I'm going to add 2 to every instance of n. Ready? So this becomes n plus 2, n plus 1, a sub n plus 2 times x to the n. I increased every instance of n by 2. So this was previously n times n minus 1. Now it becomes an n plus 2 times n plus 1. This was previously a sub n. Now it's an a sub n plus 2. This was previously an n minus 2. Now it's just an n. But I can't just add 2 to my index. I can't just add 2 to every instance without decreasing this by 2. So everything here leveled up by 2. But this got downgraded by 2. So I say n leveled up by 2. Every instance went up by 2, but the index has to go down by 2 to preserve the balance there. Okay? Now all the powers are the same. We're all pretty damn good, except for the fact that now what's weird?
The middle index is 1.
This middle index is 1, which means he's farther along already than these guys, so they need to play catch-up. So here's what we're going to do. What's the first term from this guy?
A sub 0.
A sub 0. A sub 0 times x sub 0 is just a sub 0, right? So what we're going to do is say this. What I did is I just took the a sub 0, the first term, and I plucked it out of the series and put it. I mean, you're going to be over here. So remember, a series is a whole list of terms.
Mm-hmm.
I'm going to, and this guy represents the whole list of terms. So I'm going to pluck the a sub 0 from this summation, put him over here, and then instead of starting the summation at 0, I start at where?
1.
What term will I pluck from here? It's kind of a pain. Plug in 0, what do I get? 2 times?
2 times 1 times
A sub?
A sub 2.
Mm-hmm. So 2a sub 2, and that would be the first term, right? 2a sub 2. So I'm going to pluck 2a sub 2 from this guy, but start my summation off at 1. Okay? Now, the last thing we then do, oh shit, here we go. You're going to group of powers on n in a second, but we're going to deal with these guys first. So we have 2a2 and a0. So the relationship between the 2a2, so C-O and S-T, we have 2a2 minus a0 needs to equal 0 that we have on the right-hand side. So that means a2 equals 1/2 a0. Those are dealt with now. Those are dealt with. What's left is this. We have n plus 2 times n plus 1. Notice, we can now combine these series. Why can we combine these series? They all have the same power of x to the n. They all have the same what? Index. So we have an n plus 2. This is all, it can all come under one series umbrella. N equals 1 to infinity. N plus 2 times n plus 1. We're not going to say times 8. Oh, yeah, we will. A sub n plus 2 plus 2n a sub n minus a sub n. Now we can pull an x to the n out in front. Now what needs to happen here? This is again reminiscent of something we did earlier where this summation needs to be what? What's the right hand side of the equation?
0.
0. So we need this whole thing to be 0. Of course, if the right hand side is an extra factor of x, or x squared or an x cubed or something, we have to account for that. But for the most part, the right hand side is typically 0. Don't forget that the right hand side is an x. You have to make sure. Suppose for a moment the right hand side was an 8. Okay? Then we would say 2a2 minus a0, because these are the constant terms, that would be 8, right? Or it was 8x. We would make sure when we do the x to the 1 terms, we would say 8 for those, the x to the 1 terms. But it's 0, and it's very often 0. Just want you to make sure. Don't forget that that's there. So we have here we have a relationship between a sub n plus 2 and a sub n. That is, we can say, because this is supposed to equal 0, a sub 2, or a sub n plus 2 is equal to, here we go, buckle your seatbelts, 1 minus 2n over n plus 2 times n plus 1 times a sub n. And that gives you a recursion for what a sub. So we know a sub 2 is 1/2 a naught. Now what we can do is, what's a sub 4 then? What have I plugged in for n here to get a sub 4?
2.
2. So I get a sub 2 over here, don't I? Which we know to be 1/2 a naught. And since we plugged in 2 for n, we get to plug a 2 in for that, a 2 in for that, 2 in for that. So we get negative 3 over 2 plus 2 is 4, 2 plus 1 is 3. So we get negative 1/4 times 1/2 a naught. In short, though, this is very similar to the other way we did it. So I recommend picking a way and sticking with it. I showed you the first way of writing everything out. You just might like, that's the one I saw first, I'm going to stick with it, right? If you're trying to follow along in class, because you might see your professor start doing this, you're like, what the fuck is going on? Because you're really comfortable with the method where you're writing everything out. This is going to look confusing, but I want you to be prepared for both if your professor decides to switch interchangeably between both of them. And this method might be necessary for Frobenius, I think. So that's kind of annoying, unfortunately. Anyway, and then you can find a sub 6, you can find a sub 8, you can find What about a sub 1? Well, I guess there wouldn't be an a sub 1 because, I don't know. I don't know where he went. Oh no, a sub 1. A sub 1's given, right? Remember, when you're dealing with a second order differential equation, you have a naught and a1. Those are just not given, but those are known. We treat them as known. So a1, you find a3. 1 minus 2 is negative 1. No, sorry, yeah. 1 plus 2 is, so this 6, and then a1. Then you can find a5, and a7, and a9, and a11, and so on. Cool? Okay. Good. And by the way, let me finish this problem. Let's finish this. So I have a naught, and then I have that a2 is equal to 1/2 a naught, right? And I have that a4, what I find that to be, negative 1/8 a naught. Then I have a1, and he gives birth to a3, which is negative 1/6 a1. Let's find a5, just for good measure. a5 would be when I plug in 3 for n here, right? 3 plus 2 is going to be 5. a sub 3 is negative 1/6 a1. 3 times 2 is 6. 1 minus 6 is negative 5. 3 plus 1 is 4. 3 plus 2 is 5. So I get a 4 down here, and the 5 cancels, giving me 1/4. Negative 1/4 times the negative 1/6 over here is positive 1 over 120. Positive 1 over 24 a sub 1. So what will my series look like? Here's what it's going to look like. Y equals a0. A0 is the constant coefficient, right? Because when you're looking at the power series, y equals, you see a0 plus a1x, right? So a0 is just, when I factor it out, when I factor a0 out of a0 times 1, what do I get? Just 1. The next term is going to be, that depends on a naught, is this 1/2 a naught, that belongs to a2. So the a2 term is the coefficient of what? X squared. So I have a 1/2 x squared. What else do I have? I have minus 1/8 a naught, so that's my minus 1/8 x to the 4th. So this will go on forever. We're going to stop there. Plus, then the solution is generated by the a1s, is this guy. Remember, the a1 is the coefficient of what term?
First, okay.
So I just have x. And he gives birth to a3, is negative 1/6 a1. By factoring out the a1, I have minus 1/6 x cubed. And what else did it give rise to? It gave rise to plus 1 over 24 x to the 5th. You'll very often see solutions that look like this in the back of the book. One minus 1/2. There's the x a naught. There's the a1. A naught, and then as it depends on x squared, or all these other terms, and then you have plus a naught, or a1, I should say. Gotcha. Cool. So that's those answers look like. Cool. Sorry for mistreating your book.
Yeah, it's a mistake.
It's a lost cause, yeah.
Yeah.
Okay. So to answer your question, let me stop and start.